Look up at the stars tonight, and you are seeing only a fraction of reality. Most of the universe is built from something invisible, a ghostly framework known as the cosmic dark matter web. This is the hidden skeleton of the cosmos, a vast and mysterious network whose gravitational pull dictates the fate of every galaxy. Today, we are embarking on a journey to unravel 25 of its deepest mysteries. You will discover how this invisible architecture shapes everything we see, from the smallest dwarf galaxy to the grandest clusters. We will question what this cosmic web is made of and investigate the startling evidence that it might be tearing itself apart. What single cosmic mystery captures your imagination the most? This hidden architecture is not made of stars or gas, but of something far more elusive. The first great mystery is the nature of the dark matter web itself. Think of it as the cosmic scaffolding, an invisible framework stretching across the emptiness of space. Galaxies and immense galaxy clusters are strung along its filaments like luminous pearls on a string. We cannot see this scaffold, we cannot touch it, yet its presence is undeniable because of gravity. This ghostly web's gravitational pull is the only way we can detect it. It bends the very fabric of space-time, warping the path of light from distant galaxies in a phenomenon we call gravitational lensing. It also dictates the motion of stars within galaxies, forcing them to orbit at speeds that would otherwise tear them apart. The central challenge, the thing that makes this a profound mystery, is that this web does not interact with light in any way we understand. It does not emit, absorb, or reflect a single photon. It is the ultimate cosmic ghost, a skeleton we can only feel by the weight of its hand. That staggering gravitational pull points to an even deeper mystery, the missing majority of the cosmos. For every single atom that builds you, me, every star, and every galaxy, there is nearly 6 times more invisible matter holding it all together. We are not just surrounded by this dark substance, we are floating in an ocean of it, a cosmic reality where the world we see is a mere 15% of the whole story. This profound discovery has a history rooted in careful observation and undeniable data. Back in the 1930s, an astronomer named Fritz Zwicky was studying the Coma Cluster, a vast collection of galaxies bound by gravity. He calculated the mass of all the visible stars and gas, and then he measured how fast the individual galaxies were moving. The numbers did not add up. The galaxies were orbiting so quickly that the cluster's gravity, based on visible matter alone, should have been far too weak to hold them. Zwicky concluded there had to be a huge amount of unseen matter, what he called Dunkelmaterei, providing the extra gravitational glue. Decades later, astronomer Vera Rubin provided the definitive proof, not in a distant cluster, but within our own galactic neighborhood. She meticulously charted the rotation speeds of stars in spiral galaxies, expecting them to slow down as they orbited farther from the bright galactic center, just as planets in our solar system move more slowly the farther they are from the sun. But the data told a completely different story. The stars at the outer edges of galaxies were whipping around just as fast as those near the center. The only possible explanation was that each galaxy was enveloped in a massive, invisible halo of dark matter, a halo whose gravity was speeding up those distant stars. This realization turns our place in the universe on its head. The planets, the stars, the glowing nebulae, everything we consider to be the universe, is just the visible froth on the surface of a deep, dark sea. We are not made of the primary substance of creation. We are the rare exception, the luminous afterthought in a cosmos dominated by shadow. So the question becomes unavoidable. What is this invisible substance actually made of? This is the third great mystery, the hunt for the particle itself. For decades, the leading candidate has been a class of objects known as weakly interacting massive particles, or WIMP. The name tells you almost everything you need to know. They are thought to be massive, meaning they have substantial weight, and they interact weakly, meaning they barely touch the ordinary matter we are made of. A WIMP could pass right through our entire planet as if it were not even there, which is precisely why they are so difficult to catch, yet their theoretical properties make them a perfect fit. They would have been forged in the unimaginable heat of the Big Bang in just the right abundance to now weave the cosmic web we observe, but WIMP are not the only suspects. Theorists have proposed other candidates, each with its own strange appeal. There are actions, hypothetical particles trillions of times lighter than an electron, which could be streaming through the universe in vast numbers. There are sterile neutrinos, ghostly cousins to the known neutrinos that might decay and produce faint X-ray signals. There are even more exotic ideas, like the possibility that dark matter is made of primordial black holes, tiny black holes formed in the first chaotic moments of the universe. To find the answer, scientists have embarked on a two-pronged quest. Deep underground, in mines and beneath mountains, they have built exquisitely sensitive experiments to try and catch a dark matter particle as it drifts through the Earth. These detectors, like Lux Zeppelin and Xenon NT, are placed deep underground to shield them from cosmic rays. They use huge vats of ultra-pure liquid xenon, waiting for the impossibly rare moment when a dark matter particle might bump into an atomic nucleus and create a tiny flash of light or a minute electrical charge. So far, the silence from these experiments is profound. They have found nothing, which is itself a crucial piece of the puzzle, telling us that dark matter is even more elusive than we hoped. The other approach is to look for the indirect traces of dark matter out in space. When two dark matter particles collide, some theories suggest they could annihilate each other, producing a spray of gamma rays or other exotic particles that our telescopes might detect. We are searching for the ghost shadow, the faint echo of an interaction happening in the vast, dark spaces between galaxies. This immense challenge is a stark reminder that we are trying to identify the majority of the universe with instruments that can only perceive a tiny fraction of it. The answer is out there, hiding in the data, or perhaps in the empty silence of a detector waiting for a signal that has not yet come. Our inability to catch a single dark matter particle forces us to look back in time to the very beginning of everything. The fourth mystery asks how this ghostly cosmic web was born. To understand its origin, we must journey to the universe's first fleeting moments, a time of unimaginable energy and chaos. In that primordial fireball, the vacuum of space itself was not empty or smooth. It was a seething quantum foam, bubbling with tiny fluctuations. Particles and energy flickered in and out of existence, creating microscopic hills and valleys in the fabric of reality. Then, in a fraction of a second, the universe underwent a fantastic growth spurt known as inflation. It expanded faster than the speed of light, stretching those tiny quantum ripples to epic, cosmic proportions. Those microscopic hills became the seeds for future galaxy clusters, and the valleys became the vast, empty voids we see today. This was the imprint, the blueprint for the entire cosmic web, etched into the universe when it was less than a second old. We can still see the faint afterglow of this event. It is the cosmic microwave background radiation, a snapshot of the infant universe that shows us those exact density variations, the first whisper of the structure to come. But dark matter had a crucial advantage in this early universe. Ordinary matter, the protons and electrons that would become us, was constantly buffeted by intense radiation pressure, like a boat being tossed in a stormy sea. It could not easily clump together. Dark matter, however, was silent and invisible, unaffected by that blinding light. It simply felt gravity, and so it began to collapse first. It pulled into those stretched-out ripples, creating a vast, invisible network of gravitational wells. This dark matter scaffold grew in the shadows for millions of years, its gravitational pull patiently gathering the clouds of hydrogen and helium that would later ignite into the first stars and galaxies. Ordinary matter simply flowed into the waiting basins that dark matter had carved out. Supercomputer simulations of this process show it with stunning clarity. They start with a nearly smooth universe, apply the laws of physics, and let time run forward. What emerges is not a random scattering of galaxies, but an intricate, web-like structure, a cosmic spiderweb with galaxies clustering along its filaments, exactly as we observe. This means the grand architecture of the modern universe, with its brilliant cities of stars and immense, dark voids, was predestined by the faintest of quantum whispers, amplified by inflation and given form by the silent, gathering power of dark matter. The blueprint was set before the first star ever shone. This cosmic blueprint gave rise to a universe of stark contrasts. The fifth mystery lies in its two defining features, the dense filaments and the empty voids. Picture the dark matter web as a colossal sponge. The filaments are the solid, interconnected walls of that sponge, immense rivers of dark matter that form a gravitational highway system connecting the great cities of galaxy clusters. These are not small structures. A single filament can stretch for hundreds of millions of light years, a bridge of pure gravity across the cosmic abyss. Galaxies are drawn along these filaments, flowing toward the dense clusters at their intersections like cars on a freeway headed for a metropolis. Yet these filaments are so diffuse, their gravity so widely distributed, that if you were inside one, you would likely not feel a thing. You would be surrounded by the ghostly infrastructure of the universe, completely unaware of its presence. In stark opposition to these dense filaments are the voids. These are the empty bubbles in the cosmic sponge, the vast, desolate regions that make up the overwhelming majority of the universe's volume. A void is not just a space with few galaxies, it is a staggering emptiness, a region of space that can be over 100 million light years across and contain almost nothing. They are the true deserts of the cosmos. Here, the dark matter web is at its most tenuous, its gravitational pull too weak to gather any significant amount of gas or dust. This creates a profound mystery. Why are some voids completely barren, swept clean of even a single, lonely galaxy, while others contain a few isolated stellar islands? The answer may lie in the subtle variations of the primordial blueprint, tiny differences in the initial density of dark matter that determined whether a region would become a true void or a mere underdensity. Projects like the Sloan Digital Sky Survey have mapped this structure in breathtaking detail. Their visualizations show a universe that is not a random scatter of lights, but an organized network, a cosmic neural system with brilliant clusters of galaxies at the nodes, connected by faint, wispy filaments, all set against a background of immense, dark, and mostly empty voids. We live in a universe defined by what is absent as much as by what is present, a grand tapestry woven from both immense structure and profound emptiness. This discrepancy between simulation and observation leads us directly to our sixth mystery, a problem with a strangely dramatic name. The universe appears to be missing a multitude of small galaxies, a puzzle known as the too big to fail problem. Supercomputer models, which so accurately reproduce the vast cosmic web, make a very specific prediction about our own galactic neighborhood. They tell us that the Milky Way should be surrounded by hundreds of small, satellite dwarf galaxies, each held in its own hefty dark matter halo. Yet when we look up, we find only a few dozen. The problem is not just that these galaxies are missing, but that their predicted dark matter halos are far too massive to have failed so completely. Imagine expecting to see a bustling village around a castle, but finding only empty fields where the foundations are clearly strong enough to support entire towns. These dark matter halos have so much gravitational pull that they should have easily gathered gas and formed stars, becoming bright, visible galaxies. The fact that they remain dark and unseen suggests a fundamental flaw in our picture. Either something is preventing galaxies from lighting up within these potent halos, or our understanding of dark matter's properties is subtly wrong. One compelling solution proposes that dark matter might be warmer than we think. Our standard models use cold dark matter, where particles move relatively slowly. But if dark matter is even slightly warm, with particles moving faster, it would be less likely to clump together on the smallest scales. This would mean fewer of those massive small halos form in the first place, neatly resolving the missing satellite problem. Another possibility points to the violent history of galaxy formation itself. Perhaps fierce stellar winds from the first stars or explosions from early supernova blasted the gas out of these small halos, starving them of the fuel needed to form new stars and leaving them permanently dark. This cosmic game of hide and seek forces us to question the very rules we thought governed the birth of galaxies. Are we overestimating the power of these dark matter halos, or are we underestimating the forces that can stifle a galaxy's light before it even begins to shine? But the challenges do not end with missing galaxies. Another glaring contradiction emerges when we peer into the very hearts of these cosmic structures, a puzzle known as the core cusp problem. Our most sophisticated simulations give us a very clear prediction for the shape of a dark matter halo. They tell us that the density of dark matter should rise dramatically, forming a sharp peak or cusp as you move toward the galactic center. It should be like a steep, invisible mountain, with its most powerful gravitational pull concentrated in the core. Yet when astronomers measure the actual rotation speeds of stars and gas within small, dwarf galaxies, they find something completely different. The data points not to a steep cusp, but to a flat, constant density core. It is as if the dark matter mountain has had its peak sheared off, leaving behind a gentle, rolling hill. This is not a minor accounting error. It is a fundamental mismatch between our theoretical blueprint and the observed architecture of the universe. So, what is erasing these predicted cusps? One compelling line of thought suggests that the problem is not with dark matter itself, but with the messy astrophysics of star formation. In the early lives of galaxies, waves of supernova explosions would have rocked their cores. These stellar detonations unleash unimaginable energy, violently pushing and heating the surrounding gas. This turbulent activity could, over cosmic time, literally churn the dark matter at the center, gravitationally sloshing it around and smoothing out the sharp density peak into a shallower core. It is a cosmic blender, using the power of dying stars to mix the ghostly halo. However, not everyone is convinced this stellar feedback is powerful enough to do the job. This leads to the more radical possibility that the problem lies with our basic model of dark matter. Perhaps dark matter particles are not completely cold and sluggish. If they have even a small amount of intrinsic motion, a property known as being warm, they would be less likely to pile up so densely in the centers of halos, naturally producing the flatter cores we observe. Or perhaps dark matter particles can interact with each other through some unknown force, causing them to bounce off one another and resist being compressed into such a sharp cusp. The core cusp problem forces a difficult choice. Do we accept that the violent lives and deaths of stars are powerful enough to reshape the invisible scaffolding of the cosmos, or must we rewrite the fundamental properties of the universe's primary ingredient? The answer is hidden in the gentle rotation of the smallest, faintest galaxies, a quiet signal that our map of the dark world is still incomplete. The silent struggle between the cosmic web's gravity and a phantom force is reshaping the entire universe. For billions of years, dark matter reigned supreme. Its relentless gravitational pull worked like a cosmic contractor, patiently gathering gas and dust, spinning galaxies into existence, and weaving the magnificent filaments that connect them. This invisible architecture was built over eons, a testament to gravity's patient, unifying power, but another, more mysterious player has entered the stage: dark energy. This is not a force that pulls things together, but one that pushes space itself apart. Think of it as a form of anti-gravity, an inherent property of the vacuum of space that causes it to expand at an ever-increasing rate. For most of cosmic history, the dense concentrations of dark matter in the cosmic web were strong enough to resist this background expansion. Within galaxy clusters and along the thickest filaments, gravity held its ground, continuing to build structure even as the space between these structures stretched. But around 5 billion years ago, a fundamental shift occurred. The universe had expanded enough that the density of matter dropped, while the repulsive push of dark energy, which is tied to the volume of space itself, remained constant. Dark energy began to win the tug of war. Now, the expansion is not just continuing, it is accelerating. This raises a profound and unsettling question about the ultimate fate of the cosmic web. Will the accelerating expansion eventually overcome gravity's local grip? If dark energy continues to dominate, its influence will grow stronger as space expands further. In the far, far future, the space between galaxy clusters will stretch so rapidly that the gravitational bridges of the cosmic web will be stretched and severed. Galaxies on the fringes of clusters will be pulled away, their connections to the great cosmic cities lost forever. The universe would become a collection of isolated island universes, each drifting alone in an ever-cooling, ever-darkening void, unable to see any of the others. But is this fate absolutely certain? Perhaps dark matter's gravity can hold on in the densest knots of the web, in the hearts of the most massive galaxy clusters. These gravitational fortresses might withstand the cosmic tide, remaining as the last bastions of structure in an otherwise empty expanse. Or could the properties of dark energy itself change over time? What if this repulsive force weakens, or even reverses, allowing gravity to one day pull the universe back together? The outcome of this silent battle, a fight between the universe's primary architect and its mysterious destroyer, will determine the final chapter of everything. This silent battle between dark matter and dark energy is not just a future forecast, it is creating a profound rift in our understanding of the present, a crack in the foundation of cosmology known as the Hubble tension. At its heart is a simple but vital number, the Hubble constant, which measures how fast the universe is expanding today. You would think that measuring this one number would yield a single, clear answer. Instead, we have two, and they stubbornly refuse to agree. The first method looks back to the infant universe, using the cosmic microwave background as a baby picture. By studying the subtle patterns in this ancient light, patterns that were imprinted by the gravitational pull of the nascent dark matter web, we can predict how the universe should have evolved and what its expansion rate should be today. This cosmic ruler, calibrated by the dark matter scaffolding, gives us one answer. The second method uses the nearby universe as its guide. Astronomers observe Type 1, a supernova, which are exploding stars with a known intrinsic brightness, acting as standard candles. By measuring how much their light has stretched or redshifted on its journey to us, we can directly measure the current expansion rate. This local measurement gives us a different, faster answer. The discrepancy is small but critical, like two clocks built to the same perfect specification that slowly drift out of sync. One, set by the ancient dark matter web, ticks at a certain pace. The other, measured in our modern cosmic neighborhood, ticks noticeably faster. This is not an experimental error. It is a persistent, glaring signal that something is missing from our model. The tension suggests that the universe today is expanding faster than our best theories, which rely on the standard properties of dark matter and dark energy, say it should be. So what could be causing this cosmic speed up? Perhaps the properties of dark energy are not constant. Maybe this repulsive force is growing stronger over time, accelerating the expansion more than we anticipated. Or the issue could lie with dark matter itself. What if the dark matter particle can decay or interact in ways we have not yet accounted for, subtly changing the gravitational landscape of the cosmic web over billions of years and altering how structures form? This single number, the Hubble constant, has become a battleground of ideas. It hints that the cosmic web, the invisible architecture we thought we understood, might have a more complex and dynamic history than our simulations show. The universe's two most precise measurements are telling us two different stories about its fate, and hidden within that contradiction could be the key to a deeper truth about the dark universe. The Hubble tension reveals a crack in our cosmic model, but the original evidence for dark matter remains one of the most solid pillars of modern astronomy. This brings us to the 10th mystery, the enduring enigma of galaxy rotation. Every spiral galaxy, including our own Milky Way, behaves in a way that defies the basic laws of motion as we know them. The stars and gas clouds far from the galactic center are orbiting at astonishing speeds, speeds that should be impossible. To understand why this is so strange, picture our solar system. The planets closer to the Sun, like Mercury and Venus, orbit at tremendous velocities. Those farther out, like Neptune and Pluto, move at a much more sedate pace. This is because the Sun's gravitational grip weakens with distance. We would expect the same rule to apply to a galaxy. The stars near the bright, central bulge should be whipping around, while those in the dim, outer reaches should be drifting slowly, like distant icebergs in a dark sea. Yet when astronomers like Vera Rubin began meticulously measuring these rotation speeds in the 1970s, they found something that shattered this expectation. The stars at the very edge of spiral galaxies were not slowing down at all. They were orbiting just as fast as the stars closer to the center. It was as if the entire galaxy, from its brilliant heart to its faintest fringe, was a solid, spinning disk. This was not just a small discrepancy, it was a fundamental violation of the rules of gravity, unless there was a huge amount of matter we could not see. The only explanation was a massive, invisible halo of dark matter enveloping each galaxy. This halo is not concentrated in the center where the stars are brightest. Instead, it forms a vast, spherical cloud that extends far beyond the visible edge of the galaxy. Its immense gravitational pull is what grips those distant stars, whipping them around at velocities that would otherwise send them flying off into intergalactic space. Without this dark anchor, these majestic spiral galaxies would simply fly apart. The beautiful, pinwheel structures we see in telescope images would not exist. Vera Rubin's work provided the undeniable proof that we are not just missing a few specks of matter, we are missing the primary gravitational component of the universe itself, the hidden foundation that allows galaxies to exist at all. This single observation, the unexpectedly flat rotation curve of galaxies, forces us to accept a universe where the most dominant force is one we cannot see. The same gravitational pull that dictates a star's orbit can also warp the very path of its light, offering us a direct glimpse into the invisible. This phenomenon, called gravitational lensing, transforms the dark matter web into the universe's most powerful natural telescope. According to Einstein's theory of general relativity, mass curves the fabric of spacetime. A massive object, like a cluster of galaxies embedded in its dark matter halo, acts like a lens in this curved space. When light from a distant background galaxy travels toward us, its path is bent as it passes through this gravitational field. The result is a cosmic mirage. Sometimes the lensing is strong and dramatic. The light from the background galaxy is stretched and twisted into brilliant arcs and multiple, shimmering images around the foreground cluster, like a funhouse mirror reflection of the distant cosmos. The Hubble Space Telescope has captured countless such scenes where entire galaxies appear smeared into ethereal rings of light, a beautiful and undeniable signature of unseen mass. More often, the effect is far more subtle, a phenomenon known as weak gravitational lensing. Here, the dark matter web does not create spectacular arcs, but instead imposes a gentle, coherent distortion on the shapes of millions of background galaxies. Imagine looking through the rippled glass of an old window pane. The scene beyond is slightly stretched and sheared. Across a vast patch of sky, the subtle alignment of these stretched galaxies reveals the shape of the invisible dark matter filaments warping the space between us and them. By meticulously measuring the minute distortions in the shapes of countless galaxies, astronomers can perform a kind of cosmic cartography. They use weak lensing surveys to trace the gravitational signature of the dark matter web directly, constructing intricate, three-dimensional maps of its distribution. These maps are not built from light, but from the subtle warping of light. They show us the ghostly mountains and valleys of dark matter, confirming that galaxies are indeed nestled within immense, invisible halos and connected by vast, tenuous filaments. This technique allows us to see the unseeable, to trace the architecture of the cosmic scaffolding with our own instruments, proving that the ghost we have been chasing has a definite, mappable shape. The same gravitational warping that reveals the dark web might also be the key to hearing its voice. If dark matter is made of particles, then wherever those particles are most densely packed, a rare and silent event could be occurring. Occasionally, two dark matter particles might collide and annihilate each other, vanishing in a flash of pure energy. This annihilation would produce a burst of gamma rays, the most energetic form of light in the universe. It is a ghostly echo, a faint signal shouting that the invisible world is not completely inert. To listen for this echo, we have sent eyes into the void that see in gamma rays. The Fermi Gamma Ray Space Telescope constantly scans the entire sky, its detectors tuned to the precise energy of light that such an annihilation would produce. It stares intently at the places where the dark matter web is knotted most tightly, the dense centers of galaxies and the hearts of massive galaxy clusters where the probability of these rare collisions is highest. Imagine trying to hear a single, specific whisper in a roaring stadium. The challenge is immense. The galactic center is a cacophony of natural gamma ray sources, from spinning neutron stars to the shockwaves of supernova remnants. A potential dark matter signal is a subtle excess of gamma rays at a very specific energy, a single note rising above the cosmic noise. So far, no unambiguous signal has been found. Every potential excess has, upon closer inspection, been traced to a more conventional astrophysical source, yet the search continues because finding that one specific note would not only confirm the particle nature of dark matter, but also tell us its exact mass. The silence from Fermi is as telling as a detection, forcing theorists to refine their models and consider that dark matter might be even more elusive, its annihilations even rarer than we dared to imagine. We are left listening for a whisper that may never come, or one that is so quiet we have not yet learned how to hear it. The silent whispers of gravitational lensing found their most powerful voice in a cosmic collision 4 billion light-years away. This is the Bullet Cluster, a system of two galaxy clusters that have slammed into each other at a staggering speed. It is the closest thing we have to a smoking gun for the existence of dark matter. In this violent event, we can watch how different components of the universe behave, separating the ghost from the machine. The galaxies themselves, both the visible stars and their encompassing dark matter halos, are like swarms of bees. When two swarms collide, the individual bees rarely hit one another. They simply pass through the empty space between them. This is precisely what happened to the galaxies and their dark matter in the bullet cluster. They sailed right through the collision, barely noticing the other cluster was there, but the bulk of the ordinary matter in these clusters is not in the stars. It is in the form of a superheated, thin gas that fills the space between the galaxies. This gas is so hot it glows in X-rays, and unlike the collisionless dark matter, this gas particles do interact, slamming into each other with tremendous force. During the collision, this intergalactic gas was caught in a cosmic traffic jam. It was slowed down, heated even further, and stripped away from the galaxies, lagging far behind in the center of the merger. So, what do we see when we piece together a multi-wavelength image of this system? The optical telescopes show the two clouds of galaxies that have passed through each other. The X-ray telescopes reveal a bullet-shaped cloud of hot, piled-up gas lagging between them, but the most crucial evidence comes from the map of total mass, meticulously constructed from gravitational lensing. That map shows the peaks of gravitational pull are not with the hot gas. They are not even perfectly aligned with the visible galaxies. The greatest concentrations of mass are located in two large regions, each centered on one of the passing clouds of galaxies, far away from the stalled ordinary matter. This means the stuff that provides most of the gravity, the true cosmic anchor, is something that felt no friction, felt no collision, and passed right through. It is a distinct, ghostly substance that does not interact with light or with itself in any way we can detect, except through gravity. The bullet cluster delivers a devastating blow to any theory that tries to explain away dark matter by modifying the laws of gravity. If gravity alone were different, the mass would always follow the visible matter, the hot X-ray gas, but it does not. Here, in one of the most energetic events in the universe, the map of mass has been physically ripped apart from the map of ordinary atoms. The ghost has been caught on camera, standing apart from the machine it operates, yet the cosmic web is not built from darkness alone. For all its overwhelming power, dark matter is only the architect, the invisible hand that carves the basins of gravity. The luminous universe we actually see is made of something else entirely, the ordinary matter we call baryons. This is the stuff of stars, planets, and people, and its complex dance with the dark matter web creates our 14th mystery. As vast clouds of hydrogen gas fall into the gravitational wells of dark matter halos, they do not simply settle quietly. They collide, they compress, and in doing so, they heat to incredible temperatures, sometimes reaching millions of degrees. This hot gas can then glow in X-rays, a brilliant signature of the ordinary matter caught in the dark web's grip. Within these swirling pools of gas, the densest knots collapse under their own gravity, igniting into the first stars. But these stars are not passive ornaments, they are cosmic engines of feedback. The most massive stars live fast and die young, exploding as supernova. These stellar detonations unleash torrents of energy, blasting the surrounding gas out of the galaxy's shallow gravitational well. This process, known as baryonic feedback, is a cosmic tug of war. The dark matter's gravity pulls the gas in, while the fury of stars pushes it back out. The influence does not stop there. At the center of most large galaxies lurks a supermassive black hole. When it actively feeds on surrounding gas, it becomes an active galactic nucleus, launching jets of radiation and matter that can travel for thousands of light years. These jets can heat the gas throughout an entire galaxy cluster, preventing it from cooling and forming new stars. This is feedback on a truly colossal scale. The most profound consequence of all this stellar and black hole activity is that it can actually reshape the dark matter scaffolding itself. As enormous bubbles of gas are violently blown out of a galaxy, their sheer gravitational influence can slosh the dark matter at the core, stirring it and smoothing out the predicted sharp density cusp into a shallower, puffed-up core. This means the very stars and black holes that dark matter helped to create are, in turn, altering the distribution of their creator. The cosmic web is not a static sculpture. It is a dynamic, living system where the luminous and the shadow constantly interact. This intricate feedback loop is why supercomputer simulations are so challenging to perfect. To create a virtual universe that truly matches our observations, cosmologists must account for not only the laws of gravity and dark matter, but also the immensely complicated physics of supernova, black holes, and interstellar gas. A slight miscalculation in the power of stellar winds can mean the difference between a simulated galaxy that looks like our Milky Way and one that is completely unrealistic. The role of baryons reminds us that the universe is a conversation, not a monologue. The dark matter may have written the initial script, but the ordinary matter is an active, powerful participant, talking back and sometimes even rewriting the scenes. But the conversation between dark and light matter hides a deeper accounting error. We have now lost track of a staggering amount of the ordinary stuff. This is the 15th mystery, the case of the missing baryons. The Big Bang produced a very specific amount of normal matter, the protons and neutrons that make up every atom. We can calculate this number with high precision from the cosmic microwave background. When we add up all the ordinary matter we can actually see, the total falls dramatically short. All the stars in all the galaxies, all the glowing gas in galaxy clusters, all the planets and cosmic dust, they account for only about half of what the universe should contain. So where is the rest of the ordinary matter? It has to be out there somewhere. The leading suspect is a ghostly, superheated gas hiding in the empty spaces between the galaxies. Theorists call it the warm, hot intergalactic medium, or the WIM. This is not a cold, dark emptiness. It is a thin, searing fog of hydrogen and helium, heated to temperatures of over 1,000,000 degrees, threaded along the very filaments of the dark matter web. This gas is so hot it does not glow in visible light. It is also so incredibly diffuse that a cubic meter of it might contain only a single atom, making it 1,000,000 times less dense than the best vacuum we can create on Earth. How do you find something that is both invisible and almost not there? The hunt requires extreme ingenuity. Astronomers search for the faint imprint this gas leaves on the light of distant quasars, the brilliant cores of active galaxies. As the quasar's light travels through a filament of the WIM on its way to us, the superheated gas can absorb specific, high-energy wavelengths, creating a tiny dip in the quasar's spectrum. It is like detecting a specific kind of fog by the way it dims a single, distant streetlight from miles away. Another method is to look for the faint glow of this gas in X-ray light, but the signal is incredibly weak, easily lost in the background noise of the cosmos. Finding this missing matter is crucial because it closes the ledger on the ordinary universe. It confirms that the atoms we are made of are not an anomaly, but part of a vast, interconnected ocean of hot, tenuous gas that flows through the cosmic web, a river of fire connecting the islands of galaxies. Perhaps the entire dark matter hunt is a grand mistake, a pursuit of a ghost that does not exist. This brings us to our 16th mystery, a radical challenge to the cosmic web itself. What if the problem is not with an unseen substance, but with our fundamental understanding of gravity? The most prominent alternative is known as modified Newtonian dynamics, or MIND. Its proposal is as simple as it is profound. Instead of inventing a new, invisible particle to explain galaxy rotations, perhaps we should just rewrite the rules of gravity on the vast, dimly lit scales of galaxies. Mend suggests that gravity behaves differently when its pull becomes incredibly weak, a threshold reached in the sparse outer regions of galaxies. In this view, the force of gravity does not fade as quickly as Newton's law predicts. It gets a slight, persistent boost. This extra gravitational oomph would be enough to whip the outer stars around at high speeds, perfectly replicating the flat rotation curves that first hinted at dark matter, but without any dark matter at all. For individual, isolated galaxies, MEND is remarkably successful. It predicts these rotation curves with stunning accuracy, a fact that its proponents argue is more than just a coincidence. It feels like an elegant solution, a way to fix the cosmic books without inventing an entire missing universe, yet for all its elegance on a small scale, MEND faces monumental challenges when confronted with the larger cosmos. It stumbles badly when trying to explain the bullet cluster. Remember, in that cosmic collision, the gravitational mass was clearly separated from the visible matter. MEND, in its pure form, cannot account for this. If gravity is simply modified, the map of gravity should always follow the map of visible stars and gas. It cannot leap ahead to where the invisible dark matter halos were observed to be. MEND also fails to explain the intricate patterns in the cosmic microwave background, the blueprint for the entire cosmic web. The precise sizes and distributions of those ancient ripples require the extra gravitational pull of dark matter to grow into the galaxy clusters we see today. A universe running on MEND alone would not have had enough gravitational scaffolding to build the universe as we know it. In fact, to match these observations, even modified gravity theories often have to incorporate a form of dark matter, which defeats their original, elegant purpose. This leaves us at a scientific crossroads. Do we stick with the mysterious, invisible particle that explains the large-scale structure of the universe, but remains stubbornly undetected? Or do we pursue a modified law of gravity that works beautifully for individual galaxies, but shatters when faced with the evidence from collisions and the early universe? The very existence of this debate is a testament to how deeply mysterious the cosmos remains. We are forced to question our most fundamental assumptions, wondering if the ghost is real, or if we have simply been misreading the rules of the haunted house all along. The silent scaffolding of dark matter did more than just map the future universe, it cradled the very first light. After hundreds of millions of years of pervasive darkness, a cosmic dawn finally broke, ignited within the gravitational nurseries dark matter had built. The universe was still a simple place then, filled with vast clouds of neutral hydrogen gas. Dark matter's patient pull had gathered this gas into its first small halos, creating the proto-galaxies where the very first stars could be born. These were not like the stars we know today. They were behemoths, hundreds of times more massive than our Sun, burning ferociously bright and dying in spectacular supernova within a few million years. Their blistering ultraviolet radiation did more than just illuminate the cosmos. It began to tear apart the surrounding hydrogen gas, blasting electrons away from protons in a process called reionization. This marked the end of the cosmic dark ages and the beginning of the transparent universe we see today. To understand this pivotal transition, astronomers hunt for a specific ghostly glow from that era, known as Lyman alpha emission. As the intense light from those first stars traveled through the vast clouds of neutral hydrogen, it was subtly altered, scattered, and absorbed in ways that depend entirely on the gas's density and distribution. By mapping this faint emission, we are indirectly tracing the underlying dark matter structure that gathered the gas in the first place. It is like listening to an echo in a cavern to map the shape of the walls. The patterns in this ancient light reveal where the primordial dark matter web was strongest and how efficiently it funneled gas to create the first stellar cities. Soon, our view into this epoch will be transformed. The James Webb Space Telescope is designed to peer directly into this era of first light to see the infant galaxies themselves. It will study their Lyman alpha signatures in unprecedented detail, showing us how the cosmic web guided the birth of the very first stars and, ultimately, how the invisible architecture of the universe sparked the dawn of everything we can see. The true power of a scientific theory lies not just in what it explains, but in what it can predict. Our 18th mystery reveals the dark matter model as a great cosmic reproducer, a framework of such profound accuracy that it can build a virtual universe from scratch. Supercomputer simulations are the ultimate testing ground. They begin with a near-perfect replica of the infant cosmos, using the precise density fluctuations captured in the cosmic microwave background as their starting blueprint. They then set the clock running forward, applying the known laws of physics, with one primary ingredient driving the show: cold dark matter. For billions of simulated years, these digital universes evolve. Gravity works on the dark matter, pulling it into the subtle hills and valleys of the primordial landscape, and what emerges from this virtual Big Bang is nothing short of breathtaking. The simulations do not produce a random scatter of lights. They generate an intricate cosmic spiderweb. Vast, dark voids open up, surrounded by filaments of dark matter that stretch across the digital emptiness. At the intersections of these filaments, galaxies cluster together, forming massive hubs that mirror our own local superclusters. When we compare these simulated skies to the painstaking three-dimensional maps created by telescopes like the Sloan Digital Sky Survey, the match is stunning. The virtual cosmic web and the observed cosmic web are nearly identical in their large-scale architecture. This is a monumental success. It means that by putting an invisible, cold, and collisionless substance at the heart of our model, we can accurately foretell the distribution of galaxies across billions of light years. This predictive triumph is the single biggest reason the dark matter paradigm holds such a dominant position in cosmology. Even with its lingering puzzles like the core cusp problem and missing satellites, the model's fundamental ability to recreate the entire visible structure of the universe from its first whispers is a compelling argument that we are on the right track, chasing a real, albeit ghostly, cosmic truth. But this grand success at mapping the cosmos begins to fray when we zoom in. The 19th Great Mystery is a small-scale crisis, a growing collection of tensions that challenge the cold dark matter model right in our own galactic backyard. On the vast canvas of the universe, the model is a masterpiece, but when we examine the fine details, the brushstrokes seem to contradict our expectations. We have already encountered two of the most prominent issues: the too big to fail problem, where our galaxy is missing the swarm of small, bright satellites the simulations predict, and the core cusp problem, where the centers of dwarf galaxies are mysteriously smooth instead of sharply peaked with dark matter. These are not minor glitches. They are fundamental mismatches between the blueprint and the finished construction. So, what is the solution? Is the problem with our understanding of the luminous universe, or must we change our recipe for the dark one? One compelling path suggests the answer lies in the messy, violent physics of ordinary matter, what scientists call baryonic physics. We know that supernova explosions and stellar winds can blast through a small galaxy, pushing gas around with tremendous force. This gravitational sloshing could, over cosmic time, stir up and smooth out the dark matter at the core, erasing the predicted cusp and creating the gentle density hills we observe. It is a case of the tail wagging the dog, where the stars that dark matter helped to form are now reshaping their own invisible foundation. But is this feedback powerful enough to resolve all the small-scale tensions? Some researchers are not convinced, pointing to galaxies so faint and pristine that they seem to lack the stellar activity needed for such a dramatic makeover. This leads to the more radical possibility that dark matter itself is not the simple, cold, and collisionless particle we have long assumed. What if it has more exotic properties? One intriguing idea is self-interacting dark matter. In this model, dark matter particles can actually bounce off each other through some unknown force, much like billiard balls. In the dense center of a galaxy, these collisions would prevent the particles from piling up into a sharp cusp, naturally creating the soft cores we see. Another, even stranger candidate is fuzzy dark matter. This proposal suggests that dark matter is made of ultralight particles, so wispy that their quantum nature becomes important on galactic scales. These particles would form a vast, coherent wave throughout a galaxy, which inherently suppresses the formation of structure on small scales. It would be like trying to build a delicate sandcastle with a fluid, shifting substance. The very nature of the material prevents the fine details from holding their shape. This would explain the lack of small satellite galaxies. The choice we face is profound. Do we double down on the complexity of the ordinary universe, trusting that better simulations of supernova and black holes will eventually resolve the crisis? Or do we take these small-scale failures as a direct hint, a signal that the primary ingredient of the cosmos is something far stranger and more wonderful than a simple, cold ghost? The fate of our largest cosmic model now rests on the evidence from the smallest, faintest galaxies. Deep within the heart of almost every galaxy, including our own Milky Way, lies a supermassive black hole, a gravitational monster weighing millions or even billions of times more than our Sun. The 20th mystery asks a profound question: did dark matter itself help to create these cosmic behemoths? The standard story says these giants grew from the remnants of the first massive stars, which then merged and fed on gas for billions of years. But there is a problem. Some of these black holes are found so early in the universe's history, they simply did not have enough time to grow so large from such small beginnings. So how did they get so big, so fast? One tantalizing possibility is that dark matter provided a head start. In the dense central regions of the first dark matter halos, the gravitational pull might have been so overwhelmingly strong that vast clouds of dark matter could have collapsed directly, bypassing the star formation stage entirely. This direct collapse would have created massive black hole seeds from the very beginning, giant infants ready to feast on the surrounding gas and grow into the supermassive objects we observe. These primordial seeds, forged from the universe's primary invisible ingredient, would have had the mass needed to explain the giants we see in the early cosmos. But the relationship might also work in reverse. Once a supermassive black hole is established, its incredible gravity could drastically reshape its immediate dark matter environment. Theorists suggest that the black hole's pull might draw in a vast crowd of dark matter particles, creating an intensely dense region around it, a so-called dark matter spike. This spike would be a halo within a halo, a sharp peak of invisible matter centered directly on the black hole's event horizon. If dark matter particles can indeed annihilate each other upon contact, such a dense spike would become a brilliant beacon of gamma rays, the brightest possible signal in the entire sky. Yet when we point our gamma ray telescopes at the galactic center, we see no such unambiguous beacon. This puzzling absence forces us to question the theory. Perhaps the violent dynamics of the galactic core, with stars swinging past the black hole in close orbits, regularly scatter and disrupt the dark matter, preventing a stable spike from ever forming. Or maybe the properties of dark matter itself mean it cannot pack so densely. The silence from the center of our galaxy is a clue. telling us that the dance between the universe's greatest darkness and its most absolute blackness is far more complex than we first imagined. These small-scale puzzles and cosmic giants highlight a vital truth. Cracking the code of the cosmic dark matter web demands a unified front, a strategy known as the multi-messenger approach. We can no longer rely on a single type of observation. The ghost is too clever, its traces too faint for any one instrument to capture. The solution is to combine every tool in our scientific arsenal, listening to the universe across the entire spectrum of information it provides. This means using traditional telescopes that see in optical light, X-rays, and radio waves to map the luminous matter caught in the web's grip. It means deploying gravitational wave detectors to feel the ripples in space-time from cataclysmic events, like the mergers of black holes and neutron stars. It involves building vast neutrino observatories to catch these ghostly particles that stream unimpeded from the universe's most violent engines, and it continues with the deep underground experiments, patiently waiting for the direct ping of a dark matter particle. The real power emerges when we combine these different messengers. Imagine a gravitational wave observatory detects the distinctive chirp of two primordial black holes colliding. Theorists have wondered if these could themselves be made of dark matter. That single signal by itself is just a data point, but if at that very moment a gamma-ray telescope sees a specific flash from the same patch of sky, and a neutrino detector registers a coincident burst, a pattern begins to form. We could then cross-reference all these signals with a detailed, weak lensing map of the dark matter in that region. Does the event occur along a particularly dense filament of the web? Does the energy of the particles match what we would expect from dark matter annihilations? By layering these independent lines of evidence, we can triangulate the truth. A signal that is ambiguous in one channel becomes undeniable when confirmed by another. This multi-messenger strategy turns the entire cosmos into a single, interconnected laboratory. We are no longer just looking at the universe, we are listening to its vibrations, feeling its ripples, and catching its most elusive particles, all in a coordinated effort to finally see the shape of the shadow. This grand multi-messenger search is about to be supercharged by a new generation of cosmic cartographers. The 22nd mystery asks how our map of the invisible web will change when we can see it with 1 billion points of light. Our current charts are like the first rough sketches of a new continent, detailed in small areas but lacking the scope to see the entire empire. Soon, 3 revolutionary observatories will launch us into a new era of dark matter mapping. The Vera C. Rubin Observatory, now poised on a Chilean mountaintop, will conduct the legacy survey of space and time. Every few nights for a decade, its immense mirror will capture the entire southern sky, not as a static picture, but as a deep, dynamic movie. It will catalog tens of billions of galaxies, measuring the subtle, coherent warping of their shapes caused by weak gravitational lensing. This will give us not just a snapshot, but a time-lapse of the dark matter web's evolution. Joining this effort from the quiet of space is the Euclid telescope. Free from the blurring effects of Earth's atmosphere, Euclid will measure the shapes of billions of galaxies with exquisitely precise optics, creating a 3-dimensional tomographic map of the cosmic scaffolding. Its mission is to trace how the web's structure has grown and tightened over the last 10 billion years. Then comes the Nancy Grace Roman Space Telescope, with a field of view 100 times larger than the Hubble Space Telescopes. Roman will perform vast, high-resolution surveys, peering back to the universe's childhood to see how the first filaments of the web began to pull matter together. Together, these instruments will transform weak lensing from a statistical hint into a precise science. They will measure the dark matter web's gravitational warping across hundreds of millions of galaxies, allowing us to trace the thickness of its filaments and the depth of its voids across cosmic time. This torrent of data will do more than just confirm our models. It will look for the cracks. By comparing the growth of the web over billions of years to the expansion history of the universe measured by dark energy, we can perform the ultimate test. Does the dark matter web evolve exactly as our cold dark matter model predicts, or are there subtle deviations, tiny kinks in the cosmic scaffolding that point toward a more exotic truth? Perhaps we will find that the filaments are slightly thicker or thinner than anticipated, a sign that dark matter particles can interact or decay. Maybe the web's growth will reveal that dark energy's push has changed over time. We are on the verge of moving from simply knowing the web is there to understanding its every thread and knot, and in its intricate design, we may finally read the true nature of the ghost that built it all. Our very existence may be built upon a cosmic fossil. The 23rd mystery asks if dark matter is more than just an invisible substance, if it is a pristine relic from a hidden chapter of physics. Most theories suggest these particles were forged in the unimaginable heat of the Big Bang, created alongside the protons and electrons that would become us. But then, almost immediately, they decoupled. They stopped interacting with the normal matter and radiation, fading into the background as a silent, stable population. This early divorce is what makes dark matter so special. While ordinary matter was constantly buffeted by radiation, smashed together, and transformed into the complex elements of the periodic table, dark matter remained aloof. It did not get swept up in the chaotic evolution that followed. It simply was, and it simply remained. This means the dark matter web could be a time capsule, a fossilized imprint of the universe when it was less than a second old. It holds within its distribution the untold secrets of physics at energy scales we can only dream of reaching in our particle colliders. The Large Hadron Collider smashes protons together at tremendous speeds, but the energies involved in the first instance after the Big Bang were trillions of times higher. Dark matter could be our only direct link to that primordial frontier, a messenger from a realm of physics governed by forces and symmetries we have not yet discovered. Its very existence and its specific properties might be the only surviving clue to a much grander theory of nature, one that unifies all the fundamental forces. By studying the ghostly architecture of the cosmic web, we are not just mapping an invisible structure, we are reading the fossil record of the cosmos itself, trying to decipher the laws written in the first moments of time. This apparent fine-tuning of the dark matter density presents one of the most speculative and profound mysteries of all. The amount of dark matter in the universe seems to be exactly right for our existence. If the density of dark matter were only slightly higher, its gravitational pull would have been far too strong. The cosmic web would have condensed with violent speed, collapsing into a chaotic mess of tightly bound structures long before stars or planets could ever form. Galaxies would be torn apart by their own ferocious gravity, and the universe would be a hostile, clotted place. But if the density were just a little lower, the opposite problem would occur. The gravitational scaffolding would have been too weak. The primordial gas would never have felt a strong enough pull to collapse into the first protogalaxies. The universe would have remained a dark, formless sea of hydrogen, a vast and empty expanse where no star ever ignited. In either of these nearly identical universes, we would not be here to ponder them. The fact that we exist to observe a cosmos with galaxies, stars, and planets seems to depend on this incredibly precise balance. So is this just a monumental cosmic coincidence, a 1 in a billion roll of the dice that happened to land in our favor, or does it point toward a deeper, more startling principle? This line of thinking leads to the anthropic principle, a controversial but compelling idea. In its simplest form, it suggests that the universe must be compatible with the conscious life that observes it. We should not be surprised to find ourselves in a universe whose physical constants, including the density of dark matter, are fine-tuned for life, because in a universe that was not fine-tuned, no one would be around to notice. One radical extension of this idea is the concept of a multiverse. If our universe is just one of a vast, perhaps infinite, number of parallel universes, each with its own random set of physical laws and constants, then it is no longer a miracle that we find ourselves in one where the conditions are just right. In most universes, the dark matter density is wrong, and those universes are dark, sterile, and empty. We simply live in the one rare bubble where the numbers lined up to allow for galaxies, stars, and ultimately, observers. This idea pushes the mystery of the cosmic web into truly philosophical territory. Are we the beneficiaries of a single, unimaginably lucky accident? Or are we living in just one room of a cosmic mansion with an infinite number of doors, most of which lead to nothingness? The ghostly architecture that cradles our galaxy might be more than just a physical structure. It could be the ultimate signature of our own place in a much wider and far stranger reality. Our journey through the shadows of the cosmos brings us to a final, profound question. What is the ultimate fate of the dark matter web itself? The grand architecture that gave birth to galaxies will not endure forever. Its destiny is locked in a silent battle with dark energy, the phantom force accelerating the expansion of space. For trillions of years, this expansion will continue to accelerate, stretching the very fabric of the cosmos. The growth of the cosmic web, which has been building structure for billions of years, will first slow, and then it will stop entirely. The gravitational pull of dark matter, so potent on local scales, will be overwhelmed by the relentless push of the vacuum. One by one, distant galaxy clusters will be dragged beyond our cosmic horizon. Their light, stretched to wavelengths beyond detection, will simply fade from view, as if a great curtain is being drawn across the universe. The brilliant cities of the cosmic web will vanish from the sky, not by exploding, but by receding into an unreachable distance. What will remain is our own local group of galaxies, bound together by gravity into a single, massive elliptical galaxy, itself an isolated island within a fragment of the original dark matter scaffold. We will be marooned in a vast and ever-cooling emptiness, a lone structure in a cosmos that is otherwise dark, silent, and utterly empty. This is the final mystery of the dark matter web, a story that begins with a quantum whisper and ends in near-total isolation. The ghostly skeleton that built our universe will become the last relic we can perceive, a final monument to a time when the cosmos was bright, crowded, and full of light. From the ghostly nature of the particle itself to the ultimate fate of the cosmic web in an accelerating universe, these 25 mysteries weave a story far grander than we ever imagined. This invisible web is not merely a scientific puzzle to be solved, it is the fundamental architecture of reality, the hidden stage upon which the entire cosmic drama plays out. Its gravitational whispers dictated where the first stars would ignite and where great galactic cities would rise. Its silent presence holds the key to our cosmic origins, shaping the past that led to us, and it will govern our ultimate destiny in the cold, dark eons to come. Every question we have asked, from the smallest missing satellite to the largest void, is a thread leading back to this dark foundation. The universe is whispering its secrets in the language of gravity and light. It is up to us to listen. What mystery fascinates you the most? Let us know in the comments below, and do not forget to subscribe as we continue to unravel the cosmos together.